This video documents the Environmental Engineering Capstone project for the fall 2011 semester at San Diego State University. The team is made up of Nicole Marie Salem, Melody Dinkin, Justin Farron, Sharon McDonald, and Leslie Senf. The design team was tasked with creating a mixed bed ion exchange unit that would remove at least 90% of the ions present in the feed water supplied by Swiss Water Group. The team designed the apparatus, provided a regeneration method, and constructed a working prototype unit.
Laboratory analysis. In order to meet the treatment goals, the composition of the feed water must first be characterized. This was achieved by performing lab analysis to determine the pH, alkalinity, hardness, solid analysis, and ion chromatography analysis, also known as IC analysis. From the experiments, a pH of 8.46 was found. The total solids were determined as 310 milligrams per liter and made up almost entirely out of dissolved solids. This means that the suspended solids will not need to be pre-filtered to prevent pump failure or column clogging. There was a total alkalinity of 97.3 milligrams per liter as calcium carbonate and a total hardness of 129 milligrams per liter as calcium carbonate. Alkalinity and hardness were used to help estimate the concentration of ions that would be determined by the IC analysis. The IC analysis found a total of roughly 8 milliequivalents per liter of ions in the sample. The ion concentration will be used to size the unit. Ion exchange theory.
In a mixed bed ion exchange unit, both cation and anion exchange occur within one filtration column. When both cation and anion exchange take place with hydrogen and hydroxide functional groups, deionization is achieved and high purity water is produced. The driving force of ion exchange is electrostatic forces. However, this is not a strong force. In result, ion exchange can be reversed relatively easily for regeneration. Mixed bed units are ideal to separate bed units because they require less space and in some cases have higher treatment efficiencies. Ion exchange systems can be found in all stages of water treatment, including drinking water, wastewater, and industrial water treatment.
Ion exchange resins.
Selecting the right ion exchange resin is of the utmost importance to the success of the unit. Because we are removing ions from the water, it is necessary to select resins with hydroxide and hydrogen functional groups. The unit will be a packed bed column, so the resin should be of a gel polymer base as well. Resins from Purolite were selected by the team. 2 resins were chosen for the prototype application: UltraClean UCW 5072 and UltraClean UCW 9126, which are designed to work in a mixed bed together. 5072, the anion resin, has a minimum capacity of 1 equivalents per liter, a moisture retention of 55 to 60%, a diameter size of about 605 micrometers, and a specific gravity of 1.07. The 9126, the cation resin, has a minimum capacity of 1.9 equivalents per liter, a moisture retention of 49 to 54%, a diameter size of about 610 micrometers, and a specific gravity of 1.21. The difference in specific gravity allows the bed to separate completely during backwashing. The anion resin will float to the top and the cation resin will sink to the bottom. This ensures that the 2 resins will not be cross-contaminated by the chemicals used in the regenerative process.
Breakthrough curve analysis.
The actual capacity of the column bed to remove ions can be determined by conducting a breakthrough curve analysis. Once all the ions present in the surface of the resin substrate are exchanged, the bed is said to be exhausted. Recalculating the prototype capacity. The prototype was initially sized using the capacities provided by Purolite, the concentration of ions in the feed water, the flow rate, the diameter of the column, and the design runtime. The volume of water treated was determined to be 360 gallons. Hydraulic retention time was calculated as 2.4 minutes. The volume of the bed was determined to be 10.8 liters, with 3.5 liters cation resin and 7.4 liters anion resin. The constructed prototype has a column height of 56 inches containing 9 liters of mixed resin. Using the data collected from the breakthrough curve analysis, the observed resin capacity was calculated as conservatively as 0.805 milliequivalents per liter. This results in 805 liters of water treated for 212 minutes for the prototype unit.
Prototype construction.
1-inch Schedule 40 PVC pipe was used throughout the unit. Ball valves with T's were used to allow the flow to be reversed for backwashing and regeneration. Joints were prepared by light sanding with PVC primer. PVC cement was used on all joints to ensure strength and a watertight seal. The column used for the resin has a 4-inch outside diameter and 3.75-inch inside diameter. The 1-inch to 4-inch expansion for the connection of the water pipe to column was accomplished with a rubber coupler. This, along with a threaded joint at the bottom of the column, allows for easy removal. Nylon mesh was put in between 2 metal drain plates and serve as a diffuser and a filter to hold the resin inside the column.
Prototype unit regeneration.
By far the most difficult task for the team was preparing a method for regeneration of the mixed bed. Although utilizing a mixed bed offers many advantages, it does make it difficult to regenerate because the cation and anion resins each require different regenerative chemicals, and these chemicals may not cross-contaminate. One of the advantages of using the separable mixed bed resin we chose is that the bed may be regenerated upon exhaustion without cross-contamination and without disposing of resin, which can be very costly. The specific gravity of the anion resin is 1.07, and the specific gravity of the cation resin is 1.27. This means that when the bed classifies, the anion and cation resins will separate. In this manner, regenerative chemicals may be applied separately. The manufacturer recommends draining the bed 4 to 5 centimeters below the top of the bed after rinsing and applying backflush air to mix the resins once again. Because of time and budget constraints, our prototype is not designed for this type of regeneration, but we were able to come up with our own method of regeneration per manufacturer specifications.
Sizing up the prototype design. Considering sizing up this design, many other factors must first be considered, including but not limited to the amount of space available for the unit, the characteristics and variation of the feed water, and how often you want to regenerate the unit. So the unit will be able to withstand the regeneration chemicals, a Teflon mesh should replace the fabric mesh used in the unit.
We would like to thank our professor, Dr. Fatih Büyüksönmez, our lab director, Dr. Yuxin Wu, for all their help and guidance through this process, Swiss Water Group for financial support and supplying the feed water, and Purolite generously supplying the resin for our ion exchange unit.